Welcome everyone. Today I'm going to talk about AI for quantum dynamics of molecules in space. This talk is also in, yeah, so I'm going to repeat this. Welcome everyone. We are going to talk about AI for quantum dynamics of molecules in space. I'm going to discuss mostly the work of PhD thesis, and also Alain will highlight parts related to the AI and quantum chemistry. Um, okay, shall I? In principle, I'm Taha Selim. I'm based in Amsterdam in the Netherlands. Okay, people are still coming.
So,
Yeah, maybe we
uh,
are too early than the time because it's 2 minutes
but
still
we, we,
left
we can
yet.
still introduce ourselves. So my name is Alain Chance. I'm based out in the outskirts. I'm in the Yvelines, which is in the Île-de-France in France. And together with Taha Selim, we co-founded Molket formally earlier in September of 2024. And we are now Molket has joined Quick in Europe, which is a consortium around quantum technologies, and QEDC in the United States. And we've both of us we have been active in the quantum arena. We have been speakers on world-class events around quantum chemistry, quantum molecular dynamics, cybersecurity, and AI. And today we are excited to introduce you to a very interesting topic and give you a glimpse of what we are trying to achieve with AI to make the most of the quantum molecular dynamics. So that's it for now. Anything you would like to add, Dara?
Yeah, so I will introduce myself as well. So I've admitted all of attendees. Now I think we have more people joining. That's great. So I'm Taha Selim. I'm based in Amsterdam in the Netherlands. Together with Alain Chance, we co-founded Molket earlier this year in Paris and France. I'm also working as a lecturer and in quantum computing at Amsterdam University of Applied Sciences. I'm also coordinating a quantum AI series in collaboration with Alexandria Bibliothèque in Egypt. But also that this series is also attended by most of prominent figures also in the Middle East and also in the States and Europe. And recently, earlier last year, uh, uh, I just defended my PhD thesis in quantum computational and theoretical chemistry. And the work that I'm gonna present today was based on the work that has been done during the PhD. So I'm gonna highlight. So let me just admit Joe. Okay. Okay, so now before we start, what's our mission statement? So we aim for AI for accelerated chemical design and quantum simulations. Uh, so Helen, would you mind approving this? Yeah, thanks. Or shall I admit them myself?
I can do it.
I
Oh,
can do too.
okay, yeah, thanks. Yeah, because they pop in the front of the screen. Yeah, okay, that's great. Thank you. Okay, so I'm gonna now present this slide. It's about our mission statement, and it is about how AI could be used to accelerate chemical design and the quantum simulations. In Molket, we have our purpose. We propose leveraging AI to accelerate chemical design and the quantum dynamical simulations. These AI applications can be trained on the inputs and the outputs of quantum chemistry and the quantum dynamics algorithms, effectively replacing these computationally expensive components. And also, we can learn and use these AI applications to learn about the behavior of these molecular and atomic systems so they can scale these algorithms and enabling extrapolation to larger systems. Having said that, I would like to present the outline, and mainly I'm gonna start with discussing quantum molecular dynamics and James Webb Space Telescope. That was a main topic of my PhD thesis, and the title of this thesis was Quantum Dynamics of Molecules in Space. And after that, I'm gonna present the simulation or simulating nuclear collisions of CO2 helium. It should be appear here, but it's not. I think it's a problem in the rendering of the equation. And the third section will be about overcoming computational challenges with AI. Coming to the first section, quantum molecular dynamics and the James Webb Space Telescope. We all know now James Webb Space Telescope. It's a famous telescope that has been launched recently. It's now sitting at one of the famous Lagrangian points where the gravity is almost balanced. And James Webb Space Telescope is aiming to observe things with high resolution, in particular in infrared region for molecules that present in interstellar media and also relevant to organic chemistry on Earth and other planets. What we see here is depicted an illustration for the James Webb Space Telescope. It observes the infrared spectra coming from distant planets and distant interstellar media. And of course, thanks to the capabilities of James Webb, we receive a spectra, and in this spectra, atoms and the molecules have their own unique properties in the fingerprints on the spectrum. So from the spectrum, we can see the fingerprints of different atoms and species, and from that we can identify a lot. This is a bigger image for James Webb, and James Webb Space Telescope has a powerful near and mid-infrared observational capabilities. And in infrared in particular is very important for vibrational transitions in molecules. And of course, observing CO2, like Fermi resonance, it's all about vibrations, and rotational vibrational transitions are really dominant in interstellar media. And with such powerful telescope, they could be observed. It's very hard to observe them on Earth-based telescopes. So this is why James Webb, because it's now far from Earth, can observe this with better ability. And also thanks to the powerful instruments on board, this species could be resolved and a lot of information could be revealed around them. Let's now see what kind of information we can reveal from James Webb. Here is an example of carbon dioxide or CO2 as a quantum molecular sensor in space. So carbon dioxide is a molecule, and this molecule could be used as a sensor in a sense that any transitions that happen in carbon dioxide would tell about something that happened in this particular interstellar environment. And to decode this information, because this information sort of is encrypted in the received or recorded spectra that coming from molecules like carbon dioxide and interstellar media. So decoding them reveal information about the local temperature of these environments, but also molecular abundances, and there is more information as well. So the main goal of astronomers who are working on James Webb Space Telescope data is to decipher the encoded information in the spectra and extract the useful data for their models. We see here an illustration of recorded spectra and some fingerprints that are defined. And here, for example, we see ammonia, and here we can see a very prominent peak that represents carbon dioxide, and all in very big spectrum that records like hundreds of species on this. So why James Webb Space Telescope is important, and why we are caring about it in the PhD work, because we had in the Netherlands, we have an active Dutch astronomical network, and this network is studying in close collaboration with the International Space Station, but also NASA and the European Space Agency, ESA. They are studying the formation of planets. And the story is a classical story, or according to our understanding, planets came from a cycle that started by big nebula. These big nebula have sort of they collapse by gravity, and until the core or the central part is hot and dense enough, then a new star is born, and around this star, the remnant materials started to fall inward, and due to the conservation of angular momentum, the whole system started to rotate, and then we end up having a system like this that's really flattened with due to this spinning, and give a shape of a pizza. And these from this soup or from these ingredients in the pizza, planets are formed. And inside this environment, there is key molecules like carbon monoxide, carbon dioxide, acetylene, HCN, water, and the methane. Here is how wha- we observe this. So with James Webb Space Telescope, these key molecules could be tracked and observed in multiple species. And here we see many examples. I'm not gonna go through all of them for the sake of time, but you can see shapes of galaxies, shapes of protoplanetary disks, and materials around the stars, and so on. So that what we see, and then there is spectra that's recorded like this, and from this information should be retrieved. Here another example that's recent for modeling recorded spectra, and we see here the black line is actually the observed data from James Webb, and the filling that happen from this like light red color. That filling is actually the theoretical modeling, and this theoretical modeling is composed of inputs or numbers that represent the excitation or the excitations of all of these molecules. So we see traces in this modeling. We see all of these lines that if we combine them, we get this total model. So we see traces for example, HCN, carbon dioxide, many times in different vibrational transitions. Even we see the isotope of carbon dioxide. We see fingerprints of water and hydrogen cyanide as well, acetylene, and so on. So the combination of these numbers just to give or reproduce accurately the line emission of the James Webb. So astronomers, to retrieve this precision and to achieve it, they need inputs from theoretical chemists, and that's mainly about the collision that happen. Due to the fact that the spectra that we receive via James Webb Space Telescope, of course, we cannot travel there. We are talking about millions of parsecs. But to sample or to retrieve or to do this model, molecular astronomers need information about the collisional processes and also radiative processes. And the reason for that, the recorded spectra can be induced by either one of them, and there is always competition between these two main processes. So by collisions, if we have a molecule like carbon dioxide collide with a collision partner like hydrogen or molecule or helium, there is excitations, and the de-excitation will happen in this molecule, and the efficiency of these processes are described quantitatively by collision rate coefficients. It also could be induced by radiation, where the new star in the middle of protoplanetary disk, for example, can give radiation to the molecule. The molecule would absorb this energy, get excited, and either stimulated go to the ground state by stimulated emission or spontaneous emission. And or the efficiency of this process is described by three coefficients called Einstein coefficients. So we call them B and A coefficients. So basically, now, as molecular astronomers, in order to achieve this accurate, nice modeling of the spectra, in which they know for sure which peak corresponded to which molecule or which species in the space, they need full knowledge about these numbers. They need it very accurately. So they plug it in their model and they achieve some nice results like this. So in the thesis, we focused or we give we we paid the attention dominantly or permanently to CO2, and for the reason for that, CO2 is a key molecule in interstellar media and also in exoplanets. It has been found in several protoplanetary disks. It also exists in our solar system in Venus and in Jupiter's moon Europa, for example, and some of the recent observations in exoplanets like K2-18b, which it looks after this in this picture, or this illustrative concept picture, like Earth, basically, due to the CO2 presence and other organic species. So how we can provide these numbers about collisions? We do this by quantum molecular dynamics algorithms. And what is quantum molecular dynamics? Now we know we have a quantum chemistry. Quantum chemistry, it's mainly about the quantum mechanical treatment of electrons. And we have classical molecular dynamics, which is about how we describe the nuclei. Together, these two give the quantum molecular dynamics, which is the quantum mechanical treatments of both electrons and the nuclei. So we can, by describing electrons and the nuclei, we can describe the full electron transitions, but also vibration and rotations as well. So that's basically what we need in order to have a full understanding of the spectra coming from any molecular species. So quantum molecular dynamics provide modeling, for example, and the basis for many vital applications like quantum sensing, molecular qubits, chemical reactions, but also in chemical evolution, describing molecular collisions and the quantum control, molecular assemblers and the quantum memory and the quantum computing for sure. So there is many applications for that. So quantum molecular dynamics is really foundational science, and for that we used it to describe the collisions of CO2 in this interstellar media in order to provide the numbers that molecular astronomers need, in particular the collision coefficients. Because for CO2, Einstein coefficients are known, so now we are focusing on collision process. So now let's zoom in on carbon dioxide quickly. Carbon dioxide is a molecule that has three vibrational modes. Two of them are active or infrared active. We describe the quantum state of this molecule using five quantum numbers. The first number describe the first vibrational state. It's called the symmetric stretch, where the two oxygens goes opposite to one another while the carbon is almost doesn't move. We have the second mode, is called the bend mode, where the molecule bends in one of the plane. The two oxygens go in one direction and the carbon goes in the other. And because of this mode is degenerate, it can happen in two perpendicular planes. We describe the rotation of the plane where the molecule bends. The whole plane rotates. We describe this by a quantum number called the vibrational angular momentum. So this particular mode has two quantum numbers, one to describe the motion of the atoms, and the other one to describe the rotation of the plane where the atoms are sitting. We come to the third quantum number, is called the asymmetric, where one of the carbon and one of the oxygen atoms uh, they moved opposite one another. So we have the carbon moves, for example, to the left, and the two oxygen atoms move to the right, and vice versa. So the oxygens goes in one direction, and the carbon goes in the other direction. And we have the final quantum number is the rotational quantum number, which describes the rotational states and how the molecule rotates around its axis. Now we come to what we try to achieve. So in summary, James Webb Space Telescope detects high resolution spectra of CO2. The question is, can we simulate the collision of CO2, for example, with helium and hydrogen molecule? And the answer is yes, we can do that. But how we can do this? We can use quantum molecular dynamics, which leverages or based on the Schrödinger equation. And of course, quantum molecular dynamics provides the most accurate calculation. So there is no approximation. We just come from first principles where everything should be accurate as the theory tells. So we come to this section, simulating molecular collisions of carbon dioxide. I'm just gonna admit this person. But before that, Alain, do you have any input on this section, or do you like to add something?
Um, I think it is worth mentioning that it is challenging to replicate with a theoretical model the spectra which is observed. Now, what you've shown is an excellent fit, but there are some gaps. So it might be interesting, and this is a question for you, Taha, those gaps where the theory doesn't quite match what is observed. What is the process then to deal with those?
So yeah, thanks, Alain. So if so now, if I break down the question to two parts. So the first part, we observe things that's allowed to observe, like from the capabilities, experimental capabilities. So thanks for the question. So that's what James Webb does. Now, because thanks to these significant and phenomenal capabilities of James Webb, the spectra could be resolved and we can see peaks. Otherwise, it will be more like a homogeneous line that goes without having any defined fingerprint in the spectra. The second part of the question, what will happen if we don't have a theory to describe this? I think that's also challenging. It requires a lot of heavy work. So a lot of theory to be developed. It might take 1 or 2 years to develop a good theory. Of course, with experience, it takes less time. But for example, dealing with CO2, it sounds a simple molecule, but the amount of parity adaptations and the adaptations that exist in this molecule and the symmetry groups and all of that's a lot of work. So as we are gonna go through the presentation, we are gonna discuss, okay, maybe we can, after having a particular algorithm applied to several species, maybe that could be replaced by an AI application that's trained on this. So it removes this heavy lifting, but that's the hope.
Thank you.
So the second section, we going now for simulating molecular collisions. How we do that? I'm gonna go through quickly the technical like a study of this, but not with to discuss really the technicality, just to show you glimpse of how this work is done. And this is like a general recipe for doing such scattering calculations or quantum molecular dynamic calculations. So for now, I'm giving now an example of for a particular mode where the two oxygen atoms move in two different directions, and this mode is called the symmetric stretch mode. And of course, we can have a molecule, CO2, in a particular state, which could be the first excited state in the symmetric stretch, because we now agreed or we discussed that we have 5 quantum numbers. The first quantum number describes the symmetric stretch vibrational mode. So we have 1, it means that's the first excited state. If we have 0, it means a ground state. So that's what we see. So we have 2 energy level system basically. And if you have CO2 here, in order to study the transitions that happen from the first excited state to the ground state, that happen, for example, due to collision or induced by collision with helium. We just need to first describe the molecule and have this wave function, good wave function that describes these molecular states, molecular row vibrational states or rotational vibrational states. And of course, we have to provide solve or provide simulations that's based on quantum mechanical methods. So now we do this. We have CO2, and in this we have accurate wave functions. Then now the collision happen with helium, and in order to study what will happen here, what kind of probability or coefficient describing the transition from here to here, for example, we use a CC method, which is about solving the time-independent Schrödinger equation. So this is a particular Hamiltonian for the CO2 alone. We don't have the helium yet, so we need to have a few terms, and one important term is the nuclear motion, and then we need to have the angular momentum, the rotational part, and the potential that describes how these atoms interact with one another over a particular mode. So there is energy at a particular geometry, there is a particular interaction energy. So for example, if the molecule at this distance, at a particular normal mode coordinate, which is, we call it Q, which describes the displacement of these atoms, then we have a particular energy. So as this Q changes, at every Q, we have a particular configuration where these atoms exist in space. And for this geometry, we have uh, a particular interaction energy. So this is how we form a Hamiltonian. So you see, we need three components. We need to describe the angular momentum. So we need to have a good angular momentum. So we describe the energies of each state, of each rotational state, and we need a potential. And the potential gives rise to vibration. And so together, if we solve this, maybe we solve it using what we call variational calculations or any other method, we get wave functions that describe every state, but also the energies that correspond to each state. So we should do this or have this accurately. For high resolution spectroscopy, this has to be extremely accurate, and this is extra challenge. Now we come to CO2, will come to collide with helium. Our nice Hamiltonian of CO2 is sitting here, and we need extra terms to describe the whole system, which we call dimer. And these extra terms, we need one to describe the kinetic energy, how these two parties are coming and approaching one another, and the angular momentum of the whole system that describes when they coming to one another, they might be rotating around one another, or they couple together and then they rotate, and the interaction potential that describes also at each configuration particular geometry where CO2 is sitting somehow in space and the helium, we have a particular energy. So you see, we have a big Hamiltonian also. Each Hamiltonian needs its own theory, as we shall see in 2 minutes. So now we need to have accurate rotational vibrational wave functions. We need to have an interaction potential. That's the second term. And the interaction potential, for example, could be calculated by CCSDT level of theory. It's a quantum chemistry method, which is called coupled cluster with single and double and perturbative triple excitations. So that itself is also challenging because you need to compute these energies using a quantum chemistry package, make sure that the level of theory that you are using is good enough to reproduce the interaction energies and so on. So that's how it's done. So that particular calculation in some molecular system might be very complicated. So that's challenging. That might also take from researchers very like a big chunk of time in order to perform these complicated computation. And if we compute it now, like what we have now published a few potentials for this particular system. We need to fit it. Why we need to fit it? Because we need to have a good analytical representation, a mathematical formula that can describe the potential accurately in order to do operations on it, like to have a derivative or to do anything on it. So we need to have accurate mathematical representation of the potential. And this is usually done by fitting the potential. The fit by itself is it challenging because the fit should reproduce the original points that you have been computed with quantum chemistry package. So for example, let's imagine in some average potential we compute around 20,000 points, or for example, because in some cases computations are very expensive. And for this particular situation, we need for our fit to reproduce the original data. So the supervised learning should be done correctly, and also for our fit to reproduce the points that weren't part of the training itself or not part of the fit. So at least we can generate more points based on our need in the simulation. So if we generate for example, 10,000 points, our simulation might need 50,000. So we need to have a good fit which can probe the main characteristics and the main patterns and the potential and reproduce it. So we can have the original points, but also the points that were not included to this. So I see comment from Dave about a process which add energy to the molecule. Yes, a collision can add energy for sure to molecule and make excitations, but also it can cause disturb the molecule and make it de-excite, and that energy has to go somewhere, maybe in kinetic kick to the collision partner or radiation, for example. Yeah, for first order, that could be done, but it depends also on the use case. You might use approximation till, okay, that's enough for my case. But if you are dealing with high resolution spectroscopy or you are dealing in labs with lasers or something, then you need accurate representation, not approximations all the time. So it depends on the use case. But every approximation has its own pros and cons. Sometimes it's easy to develop theoretically, but computationally it might not sound high in the results. And if you do good work in the theory, which is time demanding, then you can get good results. So it's always a trade-off, how much time you need to spend on it and what's your expectations from the quality of data you want to produce. So here another technical slide, but to show you how this is plugged in a computer. We have basically a huge matrices, and these huge matrices, we have huge matrices where we have the vibrations, and each vibration level or state has its own rotational states. And because we have a system we call it dimer, like two parties, then we have the total angular momentum that describes the whole system. And then we get this omega quantum number with the eigenvalue of the simultaneous projection of the rotational vector of carbon dioxide on the z-axis of the body frame, and of course also the z component of the total angular momentum. So we don't need to delve into the theory, but that's the take-home message here is that we have big matrices to solve in a computer. Yeah, Alain, please.
How big, how large? What do you mean by huge?
Yeah, that's a good question. So now we are talking in simple cases. It started from 10K to 15K. In some cases, it's about 30K by 30K. It's a square matrix. So that's a typical average. And maybe if we go here, we can see how this matrices grows, for example, with the state. So if we are having to converge the calculations, we might need for every vibration, we might need around from 50 to 70 rotational state. And suddenly, because we have a total angular momentum, we might have for like a small job, 5K by 5K, then an average job, 10K by 10K. Then we might have, in extreme cases, we might have 15K by 15K. So yeah, and so that's a very small system. So for large one,
And
this might be
typically, 15K by 15K, is this something one can do on a, say, powerful PC or workstation, or is it something you quickly need to have a high performance computing HPC? Any idea? I mean, is it kind of a challenge in order to access the resources that can support a kind of computation?
So that's a good question. Thank you for it. So it's always a challenge to access those resources. So most of these calculations are done on the cluster of the university, which has a good number of computers. Every computer, and we use high nodes, where every node have around almost close to 1 TB of gigaram. Because now we are talking about one single job. So typically, to do one run at a particular collision energy where these molecules approach one another, we might have, based on the parity and the total angular momentum, we might have around from 100 to 150 jobs for one energy. And typically, we need around 200 energies So that might take 2 weeks, but of course, if we parallelize on very large number of computers, as you said, like efficient HPC, it might be doable less than a week, but there is a cost involved in running those simulations. So we spend sometimes more time to in order to reduce the size of these matrices, like trying to leverage certain symmetry or parity or something that we can parallelize more. So we reduce the time that it's taking to do matrix inversions, because that's also goes to this complexity goes to the third power of with the number of equations or the size of these matrices. And hence, one job might take 1 day, and in some cases it might take 2 days. But then with doing more work on the theory, but of course it takes a lot of time to do so. We hope all the time to reduce the size, so it's affordable, but also we can have our test and runs in a much shorter time.
Yeah, and thank you, Taha. And that kind of work is to be done for every to be done again and again for every new molecule. Is it custom per molecule, or is
Yes,
there
I
a
think so.
generic way of reducing the complexity?
So that's a good question. Thank you. So in most cases, it's not generic; it's custom.
Hmm.
Some molecules by chance might have a closed nature, but in general it is not the case, and that has to be done for every molecule. So and it has to be repeated again for computing a new potential, getting accurate with functions that describe, for example, the monomer, which is in our case now CO2, but it could be HCN or another system, and doing the potential that describes the dimer or the system, and then do all of these computations again and again at all of these energies.
Thank you.
One PhD might be about one molecule,
Okay.
which is around 5 years on average. Five
Wow.
to, yeah,
Yeah.
that's and some
That
some
gives an
people start
idea
from
of yeah, that gives an idea of the trade-off between polishing the theory to and I guess there is a sense of real time because the astronomers cannot wait several years for some great theoretical work to help reduce the cost of making some simulations. So that must be very, very interesting. Um, Thank you for
so.
clarifying, Taha. Let's move on.
Yeah, and thanks, Alander. Regarding this point of the expensive hourly rate of James Webb, yeah, that's a very expensive piece of equipment. So thanks for pointing to this out. It's a very expensive piece of equipment that took about 30 years or so in development, and the funding and the investment about 30, I think, yeah, 10 billion or so from EU, but also from the states mostly, and some other space agencies. And of course now, to in order to have the data, they need to know, oh, okay, what we can do about it, and of course analyze it in real time, because there's a lot of data, and they need also to throw away some part of this data, because there is not enough storage to store all of that. So they need to focus on what is relevant for them, and these kind of calculations help astronomers to see, okay, yeah, this could be relevant, this is important, this we can analyze, and also they have to do it in a good time frame, because also this kind of equipment also have a very fixed lifetime. It's not will not live forever. So it's better to make good use of it, and analyze everything. So if they need more observations, they can ask for it, and have it in order to complete the theory, instead of waiting many years, and suddenly the instrument has to be maintained or something. So now we come to an end for this particular section. So here I'm highlighting some results of the PhD work, and this slide was part of the public presentation of the PhD defense that I have done last year. So that in these results, we showed that we developed theoretical formalisms and codes to calculate rates, and also provide this collision-induced low vibrational transitions of carbon dioxide induced by collisions with helium atoms. And in this figure, we show that, okay, how we can, with a theoretical model, which represents by all of these colors indicated by J, which this J is the initial state. So we have CO2. This is involved the bend mode in a first excited state in the first rotational state, because due to constraints and angular momentum, I'm not gonna discuss it. We cannot start from J equals 0. But then we see 10 lines, and these 10 lines, whatever initial state we have, we relax to the ground state, and the total sum of relaxation to all individual rotational states is the same. And the blue one is the experimental rates. And here the theory matches quite well with the experiment. But in order to achieve this kind of nice happy ending of the work, it took a lot of time from debugging, but also developing the theory and working on different mathematical models to be sure that we have the correct phase, the correct symmetry, correct parity, and so on. And on the right here, we see an example of a Borak cuts, this contour plot of a potential energy surface for the bend mode. And we see how the potential looks like when the molecule bends and when the molecule is still rigid, and so on. So with these two slides, we show that. Feel free to see the papers, and I'm gonna provide them in the slides on our GitHub, which Helen can send to you on your emails. Okay. Yes, we are gonna discuss this question later.
Yes,
Yes. Yeah.
the question about quantum computing, how can it contribute in enhancing this simulation process? We'll give a preliminary answer in a few slides. So
Yeah.
be patient. Yes, we will take care of that.
So, and for this, the papers and if all the with the bibliography, that will also be handed in to Helen, and then Helen can distribute on your emails yeah, the link to the slides, but also with references and everything. So now we come to the third section, and yeah, Ala will discuss it with you. Yeah.
Yes. So you've understood from Taha's presentation that there are indeed challenges in terms of computational complexity. Now, in order to present what we believe is the best practice, that there is a recent paper by Microsoft Azure Quantum, dated 9th of September 2024. And I refer to their figure number 1, which I think is outstanding. It shows a complete process. It's a flow chart of their approach, and they combine classical high performance computing, HPC calculations, which enable them to determine the so-called active space Hamiltonian. So I provide a definition of what the Hamiltonian is. It's a fundamental operator in quantum mechanics, and it represents the total energy of a quantum system. And then this is where quantum computing hopefully will eventually deliver value, but it's still a trial and error process. It's still quantum computing, in my opinion, is still a bet that will eventually be won. The question is, we don't know yet whether it will be this year, 2025, the year of the quantum science, or whether it will take another few years or maybe a couple of decades. It's an open question. But this is definitely where reliable quantum computing is supposed to play a key role, namely in constructing a quantum circuit for the relevant wave function, and simply by performing measurements, and we need a number of them in quantum computing. We need something like 1,000 measurements at least for every quantum circuit. Then in other words, the quantum computer behaves like the nature would do. So it's simulating a quantum physics, quantum molecular dynamic system with a quantum computer, which is another quantum mechanics system. But that's not the end of it. After the measurements, we end up with a so-called probability distribution. So it's classical data. And this is where we will focus in the next couple of minutes. We share Microsoft as a quantum's view that classical AI can deliver a lot of value in terms of post-processing of the data which comes out of the HPC and quantum computing computations. And it's fairly obvious why it is so expensive to get this data that the idea is that with AI, and it's I would say classical AI, we're not talking about generative AI here. We are talking about field-proven classical AI, and we will introduce the idea of surrogate models, which can mimic the behavior of a function based on a number of data points. And then hopefully, then it's just a matter of running the surrogate function, the classical model that emulates the function. Let's move on. Yes, please. Next slide. So back to the I guess it can be a bit scary for some of our viewers. This is the equation, but the important thing is to understand that there are 4 different parts. Each one of them is dealt with separately. So the goal is to obtain an accurate wave function of the monomer CO2, or equivalently to obtain an accurate surrogate model, a model that represents very accurately the physical wave function, and also to get accurate potential energy surface (PES) calculations, analytical fit. So we don't have time to go into details what a potential energy surface is. Some of our viewers might be interested to have a peek at the book I co-authored just a few years ago, back in 2022, with Dr. Kipper Alain Chance, and the book is called Quantum Chemistry and Computing for the Curious. And then there you will find a bunch of examples of potential energy surfaces. Now, we also need efficient methods to solve the CC stands for coupled cluster, equations, and reduce
Couple
the
of channels,
computational
yeah.
complexity. Yes, Taha, yes?
Yeah, a couple of the channels. Just
Oh, yeah. Yes, coupled channel, yes. Let's move on, next slide. So what about the CO2, the Hamiltonian? Again, it's the operator in quantum mechanics that represents the total energy of the quantum system. So we use, and this is still work in progress, but we have been very successful so far. We use off-the-shelf neural networks surrogate package from Julia. Julia is an interesting language which was invented, I think, about 10 years ago, a bit more, which is as cool as Python in terms of developing software, because it's interpreted, but its performance, it's close to what you could achieve with Fortran or C or C++. So it's popular in the scientific arena, and for performance reasons. And so this is what we have done. We managed to and this is again work in progress, the early results. We managed to very accurately represent potentials and vibrational frequencies, which are computed by some other means with surrogate functions. Now, these are examples. Now, you have got to take my word for it, but basically on the left-hand side, yes, there are 2 curves, 2 plots, but they are so perfectly the surrogate function is so perfect that you cannot see one, but they are superimposed. So on the right side, you can see there is a small, you can see at the top that the range plot, which represents the neural network surrogate function, doesn't quite cover the wave function, but otherwise the fit is close to perfect. Now, this is published in a notebook. Maybe during the questions and answer, we'll have the opportunity to have a peek at these Jupyter notebooks. But so it's publicly available, and we welcome our followers to make comments. So let's move on to the next slide. So there is another part which we need to accurately model. And we have achieved that with another flavor of neural network surrogate function. It's called radial basis functions. And we have accurately simulated the 1D, one dimension, and 2D, two-dimension cuts of potential energy surfaces. And we aim to extend that to 3D and 4D. There is another Jupyter notebook, which is publicly available. We have figures. I think the next slide, please, Taha. Yes. And so again, I mean, you only see one plot because the surrogate perfectly matches the potential. One of the mathematical tricks we use to achieve such outstanding fit is to rescale. So this is the reason why it's from 0 to 1 on the vertical axis. It's not a coincidence. It was done on purpose, and the important thing is that the accuracy is better than 10 to the power of -4. So the fit is there is no need to have a better fit because the data in the first place it is not more accurate than 10 to the -4. Is that correct, Taha? Yes, the data.
Yeah,
Yeah.
that's because now it is in centimeter. So in heart rate, we have the original data coming from quantum chemistry packages in atomic units or heart rates, and those have many zeros, and then the significant numbers are always at the end. So just to have them visually, and when you convert to centimeter, if you have 3 or 4 digits of data, that's like great. I mean, it's outstanding. So
Yes.
so that's why, yeah. So someone is
So
coming
someone is
in.
asking for a link. Yes, we can. I guess, Taha, you
Yes.
can answer this one. Well, let's move on to the next slide.
Yes. For Abdullah, I would, yeah, just to give
Yeah,
who's
the
yeah, and also
units.
for Aida, I will just to give you the link just in few minutes after we finish the
Mhm.
presentation. So
Yes.
okay, okay.
And of course, the kinetic energy of the dimmer, well, that is yet to be implemented. So the idea in a nutshell is to not reinvent the wheel. There are outstanding packages. A bunch of them are well known in the Python community with PyTorch, a bunch of high quality software. But what I think Taha can confirm this because that's his own experience in academia as well. I think in institution like the CERN, until recently, until I mean a couple of years ago, um, uh, at least two different programming languages were used, like Fortran or C language plus Python. Okay, Fortran and C for the performance because these are compiled languages, and Python because it's cool to develop and to glue different pieces of software. But nowadays, and at least this is something we have been successfully experimenting with Julia language. It's as simple as easy to use as Python, but the first time you run a Julia a piece of code, a function, it's interpreted, but which makes it easier to debug and get it right. But the second time it's compiled. And our own experience, mine in particular, is that the difference in performance for some scientific codes pertaining to quantum chemistry, the Julia code runs something like 50 times faster than the Python code. and almost as fast as native Fortran code, which has been optimized. So it's unoptimized Julian code. So this is really exciting. So this is the reason why, at least for this project, we have elected to use. So it's the surrogate.jl. JL stands for Julia, surrogate.jl library. And our Jupyter notebooks use these packages. Okay, so to sum it up, this is our offering. Taha and I have co-founded Molket, which has been set up as a SaaS in Paris in September of last year. We offer management consulting and AI services for quantum molecular dynamics. This was the topic of this presentation, but also cryptography. So we'll have the pleasure of talking about quantum permutation pads in some other context in the near future. So that's pertains to cryptography. Okay, neuromorphic-based computing, it's something we aim to do with Taha, but it's still very much a concept. The idea is to mimic the way we think our brain works with quantum computing concept. Maybe you can elaborate on that, Taha, about
Yeah,
neuromorphic, what we have in mind.
yeah. So thanks, Alain. So that's a very good topic, and also I love it so much because it has neuro and morphic in it. So that's a very nice topic. So the idea is that the quantum molecular dynamics it's also has its own mathematical formalism. It's very close to quantum computing. So quantum computing could be also a recasting of quantum molecular dynamics or quantum mechanics in general. So the question is, can we work with neurons as a molecular system in which we can emulate the way that the neuron think or fire a thought in this particular energy? Because now we can trace this energy through the sequence of molecules that are arranged next to one another and have an accurate simulation of that. So if we have that, then it means that we have a particular unit of thought as a code. And then if we have many units, that emulates few neurons interacting with one another. So that could open the door for a new way of computing because we just need to figure out what kind of simulation and what kind of molecular system could emulate the basic neural structure we have or we use it in our brain, for example, or maybe in like a primary creature, not a advanced one. And then from that we can use this as a unit because we have a proven use case. We already think with our minds and our brains, so that's already working in ours. So it's matter of how we can figure out the correct formalism and the correct simulation of a neuron, which is a particular sequence of molecules arranged next to one another, and have an accurate simulation using quantum molecular dynamics, which tells us how the information is inputted to a neuron and how we can have it as an output. And that could open a door for a new way of computing that's really based on neuromorphic, but not on like a GPU based neuromorphic, but no, this is based on biological neuromorphic computing.
Thank you. And so besides those services, and this is basically leveraging what we have done initially as part of I would say, workflow, a process similar to the one put forward by the Microsoft team. We are in a position to offer consulting services for training AI on data sets from fields such as chemistry, biology, material science, and cosmology, basically physics-based data or chemistry-based data. But we won't touch human. We are not in the business of dealing with text data or stuff like that. It's really our focus is on physics-based data. And so our services, they are supported by physics-based kernels quantum mechanical kernels, which concept of kernel is part of machine learning. So that enables development of advanced machine learning algorithms with significant predictive power. So in a nutshell, it's physics-inspired AI. So it's a combination of the best of breed of the art of modeling physics system using sometimes from ab initio, from basic principles, and field-proven classical AI techniques. So this is where we are today. Okay, I think there is that's the end of our
Yeah,
presentation, I
that's the end of
believe.
the presentation. We have now a question which is open for discussion. Now, after what we have seen so far and we discussed, could we have a generalized AI framework for all chemical simulations? So that's left for the question and answer. So yeah, so thanks. That's the
Oh,
presentation now is done, and there is bibliography.
yes.
Here there is a bunch of references, but the full bibliography will be published on our GitHub repo. So and we will communicate it to Helen, so Helen can share it with you, or you feel free to ask us directly on LinkedIn, and then we can share it directly with you. So
Yeah.
thank
So
you.
we
Yeah, Ala, please. Yeah.
Yeah, we can stay on this page bibliography because it's in my opinion it's interesting because all these references are fairly recent, less than 2 years ago, and basically there appears to be so many similarities between the process which has been polished for the last, I don't know, 30 or 40 years. I mean, when we are talking about quantum chemistry, I mean, quantum chemistry existed long before quantum computing was popular, or even I would say subject to hype, and but AI has evolved, I would say, separately. But now we see the convergence, at least what that we perceive, the convergence of methods or approaches, and it's really promising. But there are many more, so many interesting papers, exciting papers being published almost every week. So this is very dynamic, and I would say maybe more promising in the short term than quantum computing, which as we have seen, does have a key role to play, but only as a part of a much bigger workflow where we have HPC and AI as well. I guess the time has come for us to address questions. Um, so okay, let's see. There is a question which do you see quantum molecular analysis complementing photonic hyperspectral spectroscopy analysis? Well, that's really technical. So, Taha, can you?
Yeah. So
Yeah,
thanks for the question. So I didn't work or I don't have a deep expertise with hyperspectral spectroscopy analysis, but I would assume from the name it's something related to photonics. So quantum molecular dynamics also can describe photonic processes because it's we have quantum mechanical systems, so also light matter interactions could be is part of quantum mechanics. It's always can complement, but technically how that's yeah that's not I don't have the answer for this.
yeah. Thank you. There is another question. I think we have partially answered it, but let's have a go at it again. How can quantum computing contribute in enhancing this simulation process? So my first cut is to say quantum computing indeed has a role to play, but as a way to generate data either by digital quantum computing with the right quantum circuits, or something we haven't covered today, but not to be omitted, so-called analog quantum computing, where the idea is to somehow replicate a natural quantum physics system, but an artificial one, And this is what a bunch of teams around the world are trying to achieve. And there is at least one computer hardware vendor I'm aware of. Her name is Pascal. Their quantum computer uses neutral atoms in excited in Rydberg state, and they can configure their quantum computer to work in either digital quantum computing mode or analog. Taha, would you like to give
Yeah,
more
so
insight?
thanks Alain for the input. So I would like to complement what Alain also has said about the contribution of quantum computing to quantum molecular dynamics. So next to that, I wanted to first to highlight that it is there is a possibility like a difficult practicality to compute with quantum computing what we can do with classical now due to the way that the algorithms are formulated. And for example, when we do it with quantum computing, we need all the time to map the way that we do the solution in classical way of solving equations in quantum molecular dynamics in the way that the quantum computing does work. And the way that the quantum computer does work, we have different architectures, the one also that Alain has mentioned now. So we have different architectures of them, but all of them boils down to have a Hamiltonian that describes the type of qubits that we are dealing with. And all the time, we need to interact with quantum systems in a way that we have an input and an output. So we need to give
Yeah.
an input to the quantum system and have an output. And the way of that is to map our problem into the Hamiltonian of the qubits so we can load the initial condition in this Hamiltonian, and then when we measure, we retrieve energies that could be related to our simulation.
Yeah.
In simple cases in CO2, that's obvious because now we can compute the energy levels of CO2 using quantum computing. But when we go to the dynamics where there is a lot of dimensionality, that's not obvious at all. And that requires restructuring the way that we do the algorithm
Yes.
in a way in the same way that the qubits are working by
Yeah.
interacting with quantum system as an input and measure the output. And that's a challenging
Yeah.
theoretically. So that's a lot of theory have to be
Yeah.
developed in order to accommodate this.
Yeah, I would like to add, Taha, that and I've practical experience on that, especially co-authoring the book Quantum Chemistry and Computing for the Curious, but also attending a number of hackathons, Qiskit hackathons sponsored by IBM. So there are two different statistics, and basically nature, I mean, at least the systems we're interested in, it's fermions, okay. Well, but the most of, if not all of the quantum computers we are aware of are so-called bosonic, and so there is a price to pay for mapping the fermionic Hamiltonian to one which the quantum computer can process, and that is there are different methods, but that is expensive. And I'd say also, and this is something we pointed out in a book I co-authored back in 2022, is that the approach which has been pursued so far was to basically cast successful, I would say, classical quantum chemistry approaches into a quantum computing framework. But that is very, very expensive. You end up with having not only a large number of qubits, but also quantum circuits for the digital quantum computers, which have a depth, that is a number of gates that must be executed to perform a calculation is like several 100,000 gates, and it is at least a 1,000 order, three orders of magnitude greater than the best quantum computers can achieve today. The latest achievement by IBM is the ability to run 5,000 gates, to execute 5,000 gates, a depth of 5,000 before the qubits start to decohere. So we need at least two orders of magnitude improvement, unless, of course, some people can think about a new way of modeling the systems so that the mapping to quantum computing is much more efficient. Yeah.
And adding to this, so thanks for pointing this out, is that, for example, in the case of CO2, as Alain mentioned, we can indeed have a particular representation of the Hamiltonian that's typically done in second quantization and do the mapping to the qubits, because there is a way to map the way of we do the second quantization to the fermionic type of qubits. But however, when we do the dynamics, it's not obvious how we can, for example, translate a particular Hamiltonian where, like, for example, helium CO2, how we can express it in a second quantization in which we can have a direct mapping to qubits. So there is a way to work on that, and that's one thing. And in the case of CO2, for example, to compute the energy levels, as I mentioned, the transformation itself is expensive and might end up in a very gigantic quantum circuits that also might exceed the lifetime of the qubits or the quantum states in the qubits itself. However, there is also another approach where some researchers and also engineers believe that analog quantum computing, where you can emulate the system, would work. But that's also technically challenging because you need to make sure that the quantum system you are dealing with in a quantum computer can work as a clone or like an avatar for the quantum system that you wanted to study in reality. So yeah, it's that's a case. Hopefully, yeah, that shine some light on this question.
Thank you. So I dealt with a question which is fairly basic, but that's fine. What's the difference between electron and nuclei? So electron is a fundamental particle, at least we think it is, which is found in the so-called electron cloud, which surrounds the nucleus. A nucleus is the core of an atom, and the nucleus is located at the center of an atom. I think that clarifies this question. Let's see other questions. So what is with this one? Okay. I think I'm looking for yet
Yeah, so
unanswered questions.
for the unit, I can also highlight a bit about the unit. So we typically use in most of simulations in quantum dynamics, but also in quantum chemistry, atomic units. And the reason for that is we need to have consistency of units in all simulations. And atomic units, it is a way that you can express units that like are harmonized together. And after we do everything in atomic units, where which is length is described by Bohr, or that's a unit of the length, energy is Hartrees. Also, you can have Planck's constant in atomic units as one. So h bar, which is Planck's constant divided by 2 omega, that's one. So that's indeed a good thing because you don't have a Planck's constant anymore, and you can always have a good way of describing energies without the need to deal with Planck's constant and having a lot of fractions in your system. So, but then after everything is done, we go to the units that we are familiar with, and typically for things that related to energy, they use the wavelengths, which because now the light itself, energy of light is h nu, which is means that Planck's constant time is the frequency, and the frequency is correlated with the speed of light with the wavelengths. And from that, we can the frequency is a reciprocal of the wavelength. So this is why we can measure the energy in units of centimeter minus one, and that's way convenient. So we can translate immediately things related to light. Okay, where I can find the fingerprint of this particular molecule. So having the energy in centimeter minus one can give a direct clue about this particular case. And for that's the units, and hopefully for the atoms, I think that answered. I can also add one thing about electrons, that electrons have no volume. because some students confuse electrons with protons. Electrons are point particles, so they don't really have a volume at all. It's like really point. However, nucleus is composed of protons and the neutrons, and the protons have a volume because they are composed of quarks. Every proton has three quarks inside, and the neutrons is the same. So they have volume, but electron doesn't. And despite that, proton has a volume because it is a composite system. It's composed of three quarks, and the electron is a point particle. It has no volume. Despite this, both of them have equivalent, like absolute amount of electric charge and opposite in the sign. So the electron is negatively charged, the proton is positively charged, but they have the same magnitude.
So, Taha, I have a question for you. Have we, to your knowledge, have we, with the James Webb Space Telescope and the analysis of spectra, have we discovered new molecules or something completely unexpected? Or so far, at least in your area of quantum molecular dynamics, not talking about uh, galaxies or other things at the cosmic level.
So yeah, that's a good question indeed. So I'm not aware of any because I wasn't following the recent news of James Webb, so I'm not aware if they discovered the new molecules. However, when I before James Webb, there were also a bit of discussions about discovering some structures, some molecules that are in a structure that we cannot find on Earth, like for example something in ring, and we find it in ring on Earth, but in space it is linear, and something like this. So a typical structure that we might not find quite common on Earth.
Mm-hmm.
That's for sure. But for molecules, no, I'm not aware. That's also an interesting question. Maybe yeah, it deserves a search on NASA website to see if this is the case, because that would be very interesting.
Thank you.
A small query there, if it's okay to ask. At the beginning of your talk, you talk about the collisions of carbon dioxide with helium. So, and also talk about the modes. You refer about four modes. I was wondering if torsion modes are not considered, first question. And second is to do the randomness of the collisions. So how do you estimate the randomness of these collisions? And the third question, what is the physical output of these collisions from your studies?
Thank you. That's very nice question. The three questions actually. So I'm gonna start with so the first, what we aim from the what happened in the collision is that in CO2, when CO2 collides with a collision partner like helium molecule, or like a helium atom, it's also molecule of a single atom, and helium and the hydrogen molecule, there is certain transitions that happen. So we aim at studying the efficiency of these transitions. And for example, when the molecule absorbs energy from the collision, it will get excited. And when it loses energy, it will get de-excited. And this released energy could be coming back as kinetic energy, or released in form of radiation or something. The second question about the randomness, since now we are dealing with quantum mechanical system, you have the randomness built in a sense that when helium approaches CO2, you don't have it as a vector, you have it as a wave. So helium is like helium coming from all directions, basically, but with weighting factors, because that wave is propagated or distributed over space. And if I share the slide again, for example, the first one, if I back to the first one, just give me 1 second. If back here, yes, we have some waves like this, like the one on the cover. So you have basically waves that interfere with one another. So CO2 is treated as a wave, but also helium is treated as a wave, and they go as two waves, making some interference. and that's the model. So the randomness here coming that you don't really have a particular direction of that. You can have a plane waves which coming in one direction, but they are waves, so they are spreaded over a particular area of space. So that's what quantum mechanics takes care of. That's different from classical simulations where you really can have a trajectory and then you need to do some randomness like Monte Carlo or something similar where you have classical trajectories and you need to sample over them. But in quantum mechanically, the concept of wave function takes care of this. Another example to demonstrate this is that we deal with a rotational operator for CO2. So with the rotational state, the rotational state doesn't have a real direction. You don't really have a direction for the state. You only know the vector or the operator, which is a rotational operator, but the state itself doesn't have orientation or anything. So you cannot say, okay, as a molecule is like this. No, it rotates around. It has its vector, or the rotational vector is aligned with a particular axis. But the classical notion of a concept of a direction, it's not present because quantum mechanics takes care of this randomness inside the concept of wave function. The third question, which is also very nice about the outcome of this. So the outcome of collision is that when you do, for example, a collision with CO2, you can compute the efficiency of these transitions. That's important for a space. So the outcome is that we get what we call cross sections, and this cross section they are averaged somehow to get what we call collision rates. However, that's important. That's not important only for space studies, but it's also important for lasers, for example, because now if you have a laser, a CO2 laser or something, you need to excite, for example, the electrons, but also to excite the molecule vibrationally to high excited state, and you need to bump it down. So you need to make collisions for CO2, so to collide with helium or nitrogen, in order to depopulate the molecules from one particular state to another. So that's called the cooling. You cool the molecule, then you pump it up again and you cool, and the released energy is a laser that you get. So this kind of collision could also be used in industry where CO2 gas could be collided with nitrogen or helium in order to depopulate it or make sure that it goes down in the ground state once it goes up. So you can have the lasing effect. Otherwise, if the electron is excited and it takes so much time to go down, then you don't really have a coherent laser or anything. So this kind of transitions is important even in industry. So you have a molecule in excited state, you collide it with another collision partner, it goes down, and then you wanted to know the efficiency, which is translates how much is this process is efficient. That could be correlated with the number of molecules that will go down, and it tells you how many collision do you need in order to pump down the CO2, and the pumping it down will mean that you release the difference in energy, and this energy will give you the laser that you are looking for. So hopefully those answers satisfy
I
your
think you
question.
skipped the torsional. I was asking about the torsional. Why you didn't
Oh,
consider torsional mode? You talk about the axial bending and the rotational modes, symmetric and asymmetrical modes. And I was asking why did you not incorporate torsional?
so the torsion now we are for the molecule we have like translational motion, but also we have electronic transitions and the vibration, and we have rotational motion. These are the quantum numbers. The torsion, sort of, from my understanding, it's like you can induce it as a classical effect that can lead indirectly to excitations, but it is in it's not a direct, it's not a quantum mechanical effect that you can take in this, because now the Hamiltonian is defined over these particular categories where you have a rotational transitions, you can have vibrational transitions, and you can have translation motion, and electronic transitions. And from all of these degrees of freedom, You can combine them in a big Hamiltonian to describe the molecular state. And from that, there is no torsion yet. So the torsion will come. You can have it as sort of at one layer higher, looking classically to the system, which is not considered in these quantum mechanical calculations.
Yeah, thank
This
you.
is
Thank you very much. Good answer. Thank you very much.
hopefully that satisfy your
Yeah, I'm
yeah
satisfied.
question.
Thank you.
Yeah, thanks.
So I've answered the question, how do the particles of the nucleus of the same charge avoid repelling one another? So I answered by stating that the strong nuclear force is much stronger than the electromagnetic repulsion between protons, and that explains why the nucleus stays in one piece and doesn't fly. I don't know, Taha, if you wish to add something.
Yeah, that's a nice and just reading the question. Yes. Oh, okay. Yeah, that's nice. Yeah, that's indeed, and also protons. Of course, the protons sit thanks to this correlation between the strong forces or the which where quarks have colored charges, and also protons are fermionic. So they somehow they can sit together, but of course the colored charge is dominant. I think there is like a book about describing this, which tells you how this goes in hand. But before I going to this technical, I wanted to tell, okay, there is also question about when you have an atoms, why they don't repel one another and they can attract one another. And the reason for that, you have a dispersion forces, and the dispersion forces coming that electrons take different energy level, spins, because you have spins up and spin down. And then you can have a dispersion force that makes molecules somehow can attract one another, don't repel one another until they come closer, and then the repulsion starts to work. That's on atomic level, and on nucleus, yeah, thanks, as Anna mentioned, it's related to the strong nuclear forces there. I see another question, but I'm not sure if it's really repeated. Oh, yeah, I see. All right. Yes.
Yes, actually, the so-called strong force, because it's strong, it's the strongest of the four fundamental forces. But actually, it's a outcome of a more fundamental force between the it's between the quarks and the gluons that make up the protons and neutrons. But it's it's what is the source of this nuclear force? Did we answer that question?
Yeah.
Yeah,
So
I
I
mean,
can, yeah.
it's complicated. Thanks for the answer. What is the source of this nuclear force? Is it another particle? Well, yes. I mean, but it's quite much more complicated than so quarks were first invented was first a mathematical concept, which was a very neat way of explaining the variety of a zoo of particles. But eventually, some experiments, namely at CERN, I think another large hadron colliders, determined that the protons and neutrons are not elementary particles, and they are composite and made up of quarks. And the quarks, there are three flavors, and they come in three colors, or so-called colors, because there is a good analogy with the colors when so there is the. But anyway, it's a very interesting topic. But Taha, would you like to elaborate?
Yeah. Yeah, thanks, Alain. So I can add one sentence about this. So typically, what we see is so as Alain mentioned, the protons are composed of quarks, and that gave rise to what we call the standard model of elementary particles. The standard model of elementary particles states that we have two categories of elementary particles. One of them is called the fermions, and the other called the leptons. And the electron is an example of a lepton category. So, and the electron is a fundamental particle, so it has no structure. And the reason for that, you can have sort of the behavior of the potential goes with 1 over r, but for the proton, it's 1 over r square. So it means that there is something inside the proton, and the proton is composed of these quarks. And next to the standard model, there is also the 4 fundamental forces. So we have gravity, we have electromagnetism, and we have the weak and the strong forces. And the strong forces are the ones that glues these quarks together. So every 3 quarks where you have 3 charges of them, they come together. So the sum of this gives spin 1 of a particle. So you can have a proton, and the neutrons are as well composed of quarks. And then the governing forces at this level are the strong forces, as Alain mentioned. And when we go to the interaction between protons and electrons that coming via the electric or electromagnetic forces, so because of the charge, so in order to interact with force, you need a charge, and this charge could be of any type. So the gravity, you can visualize it as a type of a charge. So you can tell, okay, Earth has a mass, and the mass is like the charge of the Earth to interact with gravity. And also the sun has a mass, and the mass is like the charge of the sun to interact with gravity. But however, this is one type of charge. It's all attractive. There is no repulsion in it. But when we come to electromagnetic, the charge that interact, or the feature of the particle that makes a particle interact with electromagnetic, is the electric charge. And hence, electron can interact with proton via electric charges, but also they can interact because they have masses via gravitational forces also as well. Similarly for quarks, they can interact with gravity and also with strong forces as well. So it depends. So to summarize up, it depends on the particle, what kind of charges or what kind of cards the particle has to play. And for example, electron has electric charge, but also has a mass. So it can, for example, interact with 2 forces. Similarly for proton, it has mass, but also it has quarks inside, and it has electric charge. So there's 3 forces can play around for proton. So it depends on we always the time look at the charge, and that photons, for example, don't have a charge. However, they have a mass, so they can bend with gravity. But of course, you cannot tell, okay, photon you can, for example, attract them or anything by electromagnetic. You can only influence because photons are electromagnetic waves by themselves. So you can manipulate the way that the wave is propagating, but you cannot, for example, tell, okay, I will bend the photon by electric field or anything. No, you can do it by gravity to bend the light. So because they have a mass, but there is no other charges around. Of course, these theories are evolving, so they stopped for now. For some time, the field is sort of going in a steady state, but at some point, are breakthroughs were in CERN where they discover something like they announce the Higgs boson and so on. So yeah, you can also keep looking about that and learn more about how the standard model is evolving to describe the amount of experiments and the particles that are generated in CERN.
Can I ask another question? It's okay. You mentioned about the or if somehow you correlate your work, the molecular dynamics, with neurons in the brain. So I wonder, in the neurons in the brain, the neurons might communicate among themselves. There's some communication, the pass of information, and also there might be some degree of entanglement between the neurons. So I wonder, in your work on this dynamic of molecules, if there is a kind of communication of information between the molecules, not just between the two adjacent molecules that are colliding, but other molecules within the control volume and the pass of information and entanglement, this kind of thing, Charles.
So yeah, thanks for the question. It's very interesting and also very complicated by itself. So I will answer. I will give an answer that should be inexact, but without touching a neuron first, and then I will go to neurons. So the first thing, if you have a molecular system, you can always molecules can interact with one another, but also they can interact with other molecules that are in the surrounding, not particularly in the vicinity of the molecule, because of this dispersion and the van der Waals forces and all of that. So you can always have this kind of things. The second thing for neurons, particular neurons, you can have neurons are composed of molecular systems that inherit the type of interactions that you could have for a molecular system, like long-range interactions. But you can also have a charge migration where a charge can leave one molecule and goes to another. Sometimes the electronic cloud shift due to certain chemistry that's happening and so on. So the thought by itself, it is an activity in neurons. So there is like a work that happening in a neuron, which is a gigantic molecular system comparing to what we do in quantum chemistry. It's like a huge molecular system. And inside that, you can have all type of interaction, like long range between vicinities, but there is possibility to have this. There's also potential possibility of having a charge migration. You can have any kind of interaction. And in order to simulate this accurately, that type of interaction need to be described correctly, and this would mean to devise a Hamiltonian that can describe that system in order to know what kind of eigenstates the system could have and what kind of phases, because also in the simulation you can also trace the phases or try to impose certain conditions in order to trace what kind of changes would happen. So that's for any large molecular system that could be a neuron or not. For neurons, the thing that's still now of a mystery or maybe still an active area of research is the idea of a thought. Like if you have a thought, how this is fired up. Of course, this way inspired the neural networks, because you can have bases, and every base you can expand a certain function where you have weighting factors for that expansion, and that that particular uh, representation, you can have a big neural network in a kernel, which Alain has mentioned in the mission statement. In what we are looking for, we train quantum kernels. Quantum kernel, it means that the kernel has been inspired from the physics, so it has a physics kernel, and you have seen it. You can also watch my video on my YouTube channel where I try to explain the physics-inspired algorithms, how they came, and the recent award of Nobel Prize in physics in 2024, why it was awarded in this. And the reason for that, they leveraged the way that eigenvalues are sorted to store images. So they say, okay, you have this image, you can express this image as pixels, you can correlate this pixel in a function, you optimize, you find the lowest values, then you sort out these values, and whenever you have a new image, you try to optimize it, find the lowest value compared to that. And if you sort this value based with respect to the energies that are stored already in your system, you can sort of have a quick guess of what this image could be. I will also put the link for this video in the chat, so you can have more highlights about these kernels, how they are evolved. And back to neurons, so the neurons is the same. They are the same. So they have the same like a struggle of, okay, you have what's called an idea, but this is a collective activity of many neurons. Every neurons fires an energy or works with energy that's different. So there is sort of weighting factor that's when you sum, you get this total activity. But this is still of a complexity. This is why we thought, okay, maybe if we go to like a smaller level on one neuron, we know that this neuron has this particular activity. Can we reproduce this activity by an active simulation of a molecular system So we can know the input and the output of this neuron. And if we do this for one neuron, we can also generalize it to the others, and sort of we can emulate how this activity is done. So this was my initial thinking about it. Of course, scanning up the theoretical books about neuroscience, they have these weighting factors, they try to have these models, but the quantum element of it is missing. And of course, there is speculation, or sometimes maybe some papers published about entanglement, but entanglement can happen in any quantum state at a particular condition, but it doesn't necessarily mean that the idea came from entanglement or anything. We need really to have a simulation, and that simulation need to reproduce the activity that is measured maybe with a helmet or anything on the brain, so it can like trace out the activity, and we can reproduce the biomarkers that they can see in that. So it's we were trying to find if there is someone interested in that to explore a use case, because it's also a very long it's not a simple problem that need some time and need good scoping. And for sure, if we do that, it means that you can have biological neurons to compute with, because from primitive creatures, you can have small neurons, and we know, okay, this is the input, this is the output, this is what the neuron does. Can we quantify this as a logic gate or a logic process that is done? And then based on the choice of neurons, you can sort of make a small analog computer that perform a certain computation, because this is actually that's how our brains are working. So it's working already. It doesn't need a proof of concept or anything. You just need to uncover or reveal what is under the hood, how this works in reality. But yeah, that's need to be explored.
Yeah, thank you. Good
Yeah.
answer. Yeah,
Thank you.
difficult,
Yeah,
but thank you.
yeah, and feel free to reach to me, and also to Alain on LinkedIn, and maybe we can explore this further. So that could be a good point also for future talks also as well. So I see a question about, right. Yes, about the photo of the mess. Yeah, so thanks, Alain, for answering this. Yes, that's yeah,
Yeah,
that's
we
always
could add despite the fact that photons are massless, nevertheless they carry energy and
right.
with the
And the
famous
momentum, yes.
and momentum, and so because they have energy and mass equivalent, they indeed light is bent in a at this strong gravitational field, and this is one
Right.
of the famous effect that was confirmed with the movement of the Mercury planet around the Sun, which confirmed the relativity,
Yeah.
theory of relativity. Yeah.
And also the gravitational lensing, if I may add about this, gives this rise to the dark matter, and because now they found like if they measure if they calculate the total gravitational field of a particular distribution of masses, the light should go in a certain direction, but suddenly they find it goes, for example, much stronger, or a star that rotates still keep rotating with high speed, because when you go to closer to the field, you keep spinning, rotating very high, still rotating very high despite the fact that it's a larger distance. It means that there is also other missing part that contribute to gravity somehow, but not the visible like remnant or visible objects in space. That also give a rise. And for regarding the mass, because now the scientific field has concluded there is difference. We don't have a rest mass anymore. We have a relativistic mass. So only the one that's mentioned by in the equation of Alain, this HV about HC over lambda, or E equal H nu. And this one that describes the energy of the photon, and this energy is correspond to mass, but there is no rest mass. You cannot stop a photon and tell, okay, there is mass for the photon. That is doesn't happen. So the rest mass is the mass that's computed where the particle in a particular frame of reference should not move or at rest. But that has been upgraded, this concept. So you always have a photon that has a momentum and has an energy, and the energy and the mass and relativity could be affected by gravity. So, and follows the geodesic lines or the curvature in space-time, and goes to that. And when I was doing the general relativity course during my undergrad, there was a problem in the exam, which it took was open book exam, but it took 1 month to solve in a part-time basis because it has like 30 problems to solve in relativity. And one of them was about how to use a Snell law to express the geodesic. And of course, if you map Snell's law, how the light refracted in a fluid, it's like the light bends in gravitational field. So it's always there is similarities, but yeah, it needs some time to be to be figured out. Hopefully, people didn't get a strong dose of physics, and then everyone is silent after.
So there is a question, I don't know if you have dealt with this one. Can we get more feedback on quantum dynamics after the introductions? And I'm not sure. Quantum
Yeah,
dynamics.
yes. But what do you mean? I'm just
I
trying
don't
to
know. Maybe it relates to this slide where you introduced the concept of quantum chemistry, molecular dynamics, and quantum molecular dynamics, which is
Yes, I'm
the
gonna.
like the superposition of the two. Maybe we could
Yes, I'm coming to it
go
now.
down back to this slide and make
Yes, I
sure
think it's
everyone has.
here. I think yes.
Yes, this
So yeah,
is so.
yeah.
So there
So
is quantum chemistry, molecular dynamics, and quantum molecular dynamics.
and the
Yes.
quantum molecular dynamics. Now, the idea is that we have already quantum chemistry. We know how to deal with it. Because now it's about the quantum mechanical treatment of electrons. So you can, because electrons typically in these like what we call classical quantum mechanics, or like the old version of quantum mechanics, it's not relativistic. The electrons move in a time scale that is different from nuclei, so you can always make a separation of both. So you can study the treatment of electrons and study the potential energy that's generated from electrons. And the nuclei are treated sort of using classical mechanics or something similar. And then the combination gives rise to quantum molecular dynamics. So you can treat the system where the nuclei are moving, but then you have the electrons which have a wave nature in this particular frame of work. And hence you can say, okay, these electrons I could replace by a potential energy surface that's like describes how molecules are approaching one another. And from that, you can devise a dynamics, which means that, okay, you know how these nuclei are moving with respect to one another based on the interactions that are described from electrons. So hopefully this gives an idea. I can also give the paper we in the second paper we have in the thesis. We try to explain this very well, and the formalism all explained there. So I will just yeah, drop down. Feel free to reach me on LinkedIn and then just give you the link. Also, it will be in the bibliography that Helen will share with you on your emails. So you can reach to us directly to get it, or also via Helen when she sends this information on email. So is there any other questions or anything? Then yeah.
I think we have dealt with all the questions. So unless there is don't be shy unless there is another question, and I think we have anyway we are almost at the top of the second hour. So unless there is any more question, I guess we could close this session. And thank you for the audience. Thank you for the all the questions from the very basic to the quite technical. And thank you, Helen, for inviting us for this meetup, and looking forward to being in touch with a number of the people who attended this presentation. Thank you.
Yeah, so thanks everyone, and thanks Helen for inviting us as well, and thank you for asking all of these nice questions and reminding us with all of these technical goodies in the topic and so on. And feel free to reach us whenever you have a question or a use case to explore. And thank you, Alain, for moderating the session and having all of these interesting talks as well.
You're welcome. Thank you, Taha, for your brilliant presentation and explanations. It's great to have speakers who know what they're talking about and not just a superficial presentation. So I think it was very exciting.
Alain, for
Yes,
for your answers and insights and explanations as well.
Yes. So thank you, and looking forward to meeting you virtually. There are a number of networks in which we are active. So looking forward to enjoying this year of 2025. Okay. Thank you.
Yeah. Thanks everyone. Have a
Thank
great
you,
weekend. Yeah.
and goodbye.
Bye.
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 Thank you for coming, and thank you for the great talk.
Yeah. Thanks, Helen, for the organization and this nice event. And yeah, we'll keep in touch with you to give you the
Sure.
information. And then feel free also, we can also have another event later where we talk more about some interesting things. I will share with you also the YouTube channel where I explain these things. I chunk them in the YouTube channel so they are in record whenever we have a question. Then there is some explanation already there. Typically I explain a paper or something like this.
Sure. Yeah, we can have a second talk. We are open from March this year.
That's indeed will be great to have later this year.
You're welcome to come back. Yeah.
So okay. So thanks you, Helen, and yeah.
Welcome.